easiest way to come up with a set of parametric equations is to start with x. Because x is your independent variable, so it makes sense that you would start trying to write a set of parametric equations using x. What's the easiest way that you want to create a parametric equation? Chelsea?
To let x equal t.
Yeah, so just let x equal t, and now you have the x defined with a parameter of t. Literally, that's all you have to do. After you make x equal t, Chelsea, what do you do to get your y equation?
You just substitute t in for x.
Yeah.
It's y t squared minus 1.
Now it's t squared minus 4. And literally, that's it. Now you could be a little more creative. Nothing wrong with Chelsea's problems for two parametric equations. But if you'd like to challenge yourself a little bit more, then you can make x, I think my board needs calibrated a little bit, equal anything with a parameter. A parameter is a t, or a parameter is having the cosine of theta, the sine of theta. So having a third variable. So you could say, being a little more creative, maybe x is equal to 2t, because you wanted to throw in an extra number in there. So if that were the case, if you take 2t, plug it in for x, and square it, that becomes 4t squared, and then we have minus 4. That is a different set of parametric equations with the x representing 2t. So again, you could use cosine if you wanted to. X equals cosine of theta. Y is cosine squared theta minus 1. There are an infinite amount of possibilities. One rectangular equation, but parametric equations are not unique. So there are many of them that create the same graph. So both of those equations would give me the same graph of that line, y equals x squared minus 1. We would have to manipulate the t value a little bit, but they would still give us the same graph. So you'd still have a graph. So if you look at the other one, letter B, you could be really basic and just say x equals t, so then y is 1 minus t squared. Questions with that? So in number 45 and 49, they were asking you to do exactly the same thing. It just gave you a different set of equations. So you have a rectangular equation. It told you for A to use a specific parameter, and then it told you for B to use a different parameter. So they kind of gave you a starting point. But if you get both of those in x equals form, then that's your x equation, and you're just plugging that in for your y. Questions on that? So if you're asked to write a set of parametric equations, start with x. Plug a t in there, really basic. Plug that then into the y equation. So we are going to look at, let me get this first, number 61. Number 61 was a baseball problem. So center field at Yankee Stadium, and I believe the time that this book was written, I'm not sure if Yankee Stadium, the new Yankee Stadium, was built. I'll have to look that up. But it says that Yankee Stadium has a center field that is 408 feet from home plate, and it has a wall of 7 feet. So just kind of showing you, this is the information that is given. And of course, that little diagram looks exactly like Yankee Stadium. It's a pretty good rendition of that for sure. So a little baseball guy at home plate, showing you the distance to center field and then the height of center field. So part A says write a set of parametric equations that can model the path of the ball. So looking at the information a second time, in order to correctly answer part A, the speed that's given is in miles per hour. Well, we have two values for gravity. One's in meters per second squared, the other one's in feet per second squared. So you have to convert something, and if you convert that miles per hour, I dropped my pencil and it broke. Go with purple. How would you convert 100 miles per hour to feet per second, Brandon?
You convert 100 miles to feet.
So how would you convert it to feet?
You multiply 100 by 5,280.
So now that's how many feet are in 1 mile.
And
And then what else would I multiply that by to get it into seconds?
you multiply it by 3,600 because that's how many seconds are in 1 hour.
So if you remember stoichiometry from chemistry, I remember doing a whole bunch of charts and getting things to cancel. The goal is to take the miles and the hours out of the problem. So miles, hours, cancel. But to have the feet and the seconds remaining. Feet per second is what we're looking at. So then essentially you're taking 1,000 or 100 times 5,280 divided by 3,600. And that gets you a velocity of 146.67 feet per second. So that's a little bit of converting. What are you looking for to get in the problem? What do you need to take out of the problem? So then for part A, you're asked to write the equation. Those two equations that we talked about in the notes on Thursday, one for x using velocity and cosine, one for y using gravity and sine. That will be given to you, so you don't have to have them memorized. But it says take the velocity, which is 146.67, times the cosine of the angle. And I'm just going to keep that in there, because that angle is going to come out, and we're going to put a couple different numbers in it. All of that gets multiplied by t, which is time. So time affects the cosine of the angle, or is changed by the cosine of the angle, 146.67. The x one says take negative 1/2 times gravity. Well, gravity is feet per second, so that's 32. So this becomes negative 16t squared. And then again, your velocity times the sine of an angle, whatever the angle happens to be. That is all times t. And then plus the initial height. Well, the initial height is where the ball is being hit, not the height of the wall, but the height as to where the player is connecting the bat and the ball. And that says 3 feet above the ground. So this equation would get a +3. So we're going to use these two equations here and your calculator. And we're also going to build a wall. So if you can take your calculator out, I'm going to show you how to build a wall so you know how to build a wall for your homework problem tonight. You'll be asked another baseball problem. And we're going to plug in those two equations exactly as they're written with the parentheses around them and the cosine in the problem. So we're just going to be replacing the angle. We're not going to actually calculate that cosine of the angle. So the first thing I'd like you to do is we're going to build the wall. So if you go to mode first, make sure you're in degree mode. That's step 1. So make sure you're in degree mode. After you make sure you're in degree mode, hit stat, because we're going to make a wall. And when you have the stat plots on, it plots a whole bunch of dots that are randomly scattered throughout your calculator depending on the data that you enter in. I'm going to enter in the distance of the wall as my x value. And I have 4 up here. So really we're going to plot 4 points, one on top of the other. My y value represents a height of 1, a height of 3, a height of 5, and a height of 7. So essentially in the calculator, you're going to see a wall that will be built off of these points. So stat plot takes 1 point or a box in your calculator, puts another one on top of it, another one on top, another one on top. So the x is the same, it's just the horizontal distance is building up. I stopped at 7 because that's how high the wall was. Questions? Okay, so if you go to your y equals, clear out my problems. Again, use parentheses. So the first one was the 146.67. Of course, I said use parentheses and I didn't. You're using cosine. Part B had an angle of 15 degrees, so I'm going to put in 15, parenthesis, another parenthesis, and then finally the t variable should be last. So parenthesis to start, parenthesis around the angle, a parenthesis to end, and then t. The next one is negative 16t squared plus 1, how about parenthesis first, and then 146.67 sine, the angle is 15 degrees, parenthesis, t, and then plus 3. So if you have it written down in your paper, make sure you have parentheses around all that stuff that gets multiplied. So the angle with the sine or cosine and the velocity. All right, there's 2 more things that we have to do. We have to change the window. We also have to turn the stat plot on so that it actually graphs points in your graph. So if you hit second y equals, turn the stat plot on simply by hitting enter and making sure that the on is bold. And then the last thing is your window. And the window is tricky because you're going to have to come up with your own window. So time, ask yourself, how long would it really take for a home run to be hit? It's really quick. Like, it's instantaneously. They're hitting the ball. It's flying off that bat really far, fast. And it doesn't take 10 seconds to get a home run. It's really quick. So I'm going to start at -5 just to give me some time on the other side. And like +5 is probably plenty. If you want to make it 10, you can, but 10 seconds is a really long time to like sit and wait. Doesn't seem like a long time, but it truly is. The t-step, we usually keep at 0.1 unless you're told otherwise. Now the x max, I have my min at -3. The min doesn't really matter. How far does the ball have to go for it to be a home run? Brendan? 400 and?
50.
Yeah, so 408 is the home run. Give yourself some space. Make it a little more than what that horizontal distance is. So 450 sounds good. And then the y max, there we go. Think about how high would the ball go? Maybe 50 feet, maybe 60, maybe 70. Probably not 100. 100 is probably too high because it's not like it's going up and coming down. This is like a nice long line drive that's pitching at a 15-degree angle. So make it maybe 60, 65, 70, somewhere in that vicinity. But like, you're going to have to think logically, which you guys don't like to do. You don't want to think. Heaven forbid, have to think. Think about what the problem is doing, like what's happening with the ball. So I believe the last thing you want to do is probably change this to look like a ball. I'm going to keep the little path of the curve shown so that we can see what it looks like and if it truly did cross the wall. But if you keep the little tick mark next to it, then you see exactly the path that the ball has taken. And then graph it. So I have my wall out there in center field. If it doesn't pass the wall, it's not a home run. The center field was probably catching that. Chelsea.
When's this dimension mismatch?
So after you get that one to graph, the second angle was 23 degrees. So you have those extra guys down there. And then zigzag 4 over. So try the 23-degree angle using the same equation. The only thing you have to change is the angle. It's just those extra zeros. Just hit the delete button without using them. So it doesn't work with the 15-degree angle. What did you do? That's not. So 408 4 times and then 1357. So the last question of this for number 61 wanted you to kind of see if you could figure out what the minimum angle requirement would be. And this is purely guess and check. Algebraically, to find this, you need to know a little bit more. So we don't have enough information to algebraically work through the problem. However, you all have a calculator, and if you keep the equation the same, all you're doing is changing the angle. So you know it works, like it really works. It's a nice home run at 23 degrees. You know 15 degrees is way too short, so maybe cut it in the middle. What's the middle of 15 and 23? 19. So let's try 19. Again, use some logic. Think about it. Like 23 was definitely a home run. 15 was definitely not a home run. Let's try 19. So just change the angle, nothing else gets changed, and it's way easier for you to change your angle than it is for me to change my angle. And then hit graph again, because you've done the work. So here's my ball. That still hits the wall. So if you're fast and you have bad outfielders like Addie's team, then the other team probably has a home run still. Probably a grand slam because it's a lot of walking and stealing and the other team getting a lot of runs and not Addie's team. Sad. So I would say try 20. And if it works for 20 but it doesn't work for 19, then you know that it's in between those two values. And you're just plugging in the 19.1, 19.2, 19.3. Just plugging a couple of numbers in and seeing what's going on with the ball. It really helps to have the wall there, because then you physically have something to look at. Questions? So you'll have a problem very similar to that in your homework. It'll tell you what to use for the wall, so you kind of know how to build the wall. Any questions? So we're going to do two other problems using the calculator, also trying to create an equation. So like we're working on, can you create an equation? Can you then use the calculator, the device, to help you do those? So in your packet, if you just look above at example 2, which is at the top of the packet, so now we're still throwing a ball, but this ball is being thrown straight up. So I wish I would have brought in a ball today. I didn't bring in a ball. But you're taking a ball, you're just throwing it straight up, but the velocity or the initial speed of that ball is 100 feet per second. So like you're really whipping that ball with all your might up. It says you're throwing it from a height of 5 feet above the ground. It gives you the window, and I don't have part A on here, but I really should have part A. Part A, we need to write the equations. Like we need equations in order to plug stuff into the calculator to have a window. So just a reminder, that equation would be the velocity cosine of the angle times t. Or negative 1/2 gravity, velocity sine angle times t, and then plus h. You will be given those. So that information will be given. The gravity will be given, so you know what to use for gravity as well. Ben?
Will those equations also be given on the test, or will we do it?
Nope, they'll be given to you. So Brandon, if you're throwing a ball straight up, what's the angle of a ball that's being thrown straight up? 90 degrees, yeah. So we're taking 100 times the cosine of 90 degrees. 100 is the velocity. That's how fast you are throwing that ball upward. And then that gets multiplied by t. So that would be my x equation. What is the cosine of 0, or 90 degrees, not 0? 0. So the cosine of 90 degrees is 0. 100 times 0 times t is 0. So my equation for x would be 0. Question? It's just going straight up, coming back down. So you're throwing it up, and it comes back down. That's it. There's no...
It didn't go left or right.
No, it didn't go left and right. That just, if the ceiling wasn't there, it would have not went left or right and would have fell right back down. So it's not moving at all. There's no angle to it besides the straight up angle of 90 degrees. So when we go to do the y variable, we have negative 1/2 times gravity. Well, feet per second is 32. So if I take 32 times negative 1/2, it's negative 16t squared. Again, velocity is 100. The angle is 90. That gets multiplied with t. And then you're adding the initial height. Where is the ball being thrown from? Chelsea?
5 feet.
5 feet. So I had that plus 5. So like for me, I'd be throwing it from a height of about here. That's when I'd be releasing it from my hands. So Chelsea, do you know what the sine of a 90-degree angle is?
1.
Yeah. So negative 16t squared. 100 times 1 is just 100. And then plus 5. So we're going to see what happens to the ball. As it goes up, it tries to reach its max, and then as it comes back down, as we simulate that with the calculator. So going into your calculator, go back to that y equals, use the information given here. So you are given the actual window, so you don't need to guess for that. We're going to use the ball as well, but we're making one little adjustment to the window when we get there. So make sure you use the ball so you can see the ball. So we got a 0 for x. And then when you do your window, has 0 and 6.5. I'd like you to change the x min to -3. You can keep the x max at 5. If we kept it at 0, you'd only see half the ball because the y-axis is where the graph is going to go up and down, and you'd only see a part of the ball. So moving it over to -3 enables us to see all of the ball. And then the y max, apparently you're going to throw the ball close to 180 feet in the air. So make sure when you look at your equation that you have the ball, a little circle guy, so it looks like a ball, and then hit graph. So there's my ball going up, getting close to 180 feet, coming back down. Anybody not get the ball? Not have your calculator work? So the question underneath it wants you to kind of describe what happens to the ball. Oh, you just need to change this. There you go. So what happens to the ball as it's traveling vertically? Chelsea?
It's accelerating due to gravity.
Yeah, so it's accelerating due to gravity, and then as it falls back down. So it slows as it's getting to its top. It picks back up like speed as it's getting closer to the ground. And that's because of gravity. Questions? So the last thing that we are going to look at, again, another type of activity. So these are more like, what can you do with the calculator? How do these parametric equations work in the calculator, especially dealing with objects in motion? So this is all objects that are in motion. The last problem on here is talking about a long distance runner. Any of you run long distance in here? No. Alex has to run a lot on the soccer field. No, not long distance though, short distance. Nobody runs long distance. I hate running, so I don't run long distance either. It's like the worst thing you could do to your body. It's all that pounding on the pavement. It just seems horrible. Swimming is much better, right? That's better on your joints and stuff. But anyway, we have this girl named Tanya who apparently likes to run. She runs at an average speed of 8 miles per hour. So 8 miles for an hour, that seems pretty good to me. 16 miles in 2 hours, I don't know. That seems like a pretty decent pace. 2 hours after Tanya leaves, she's leaving your house. You leave in your car, a Honda, because everybody owns a Honda. Why not? So instead of running with Tanya, this would totally be me. It'd be like, see you later, friend. You have a good run. I'll pick you up. You wait for 2 hours, and then you get in your car, and you figure you probably should go pick up Tanya. The average velocity for you that you're driving is 40 miles an hour. Our goal is to figure out how long it would take you to pick up Tanya. So how far has she gone? How long will it take you to go get her, to meet her? It says use a simulation of 2 motions to answer this question. So we're going to get the calculator to graph 2 lines at the same time. Usually the calculator graphs 1 line, and then it graphs the second line. We're going to graph it both at the same time. And our goal is to figure out what point do Tanya and me meet up so that I can pick her up. How long would it take that I'd have to travel to go pick her up? The other information it says is for us for the y values to use 2 and 4. Because we are not going vertically. There is no angle that we're hitting anything out of. There's nothing being propelled. But we still have an object that's in motion, and there's still a velocity, so we can still kind of think about the same information. So this would be Tanya. So y1 for Tanya is 2. And the reason it's 2 is so that it's not on the x-axis. Because if it was 0, then you wouldn't see it on the x-axis. So putting it at 2 just puts it above the x-axis. So Tanya's velocity, 8 miles an hour. We still need to think of that same formula. So velocity cosine of the angle. In theory, if we're running just horizontally, the angle is 0, which we know in Pittsburgh that is impossible, but we'll say that it is. What would you get if you had 8 times the cosine of 0 times t? So what is the cosine of 0, Virginia? Yeah, that's just at, because the cosine of 0 is 1. So my x equation would just be 8t. So that would be my set of parametric equations for Tanya. And then for you, all of us lazy bums who are sitting on the couch eating chips as Tanya's taking her run, you are now traveling at 40 miles an hour times the cosine of 0, still the same angle. However, you leave 2 hours later. So I can't put a t here because that means I leave at the same time as Tanya. How would you write 2 hours later? Virginia?
T plus 2.
Not plus 2, because that means you leave 2 hours before Tanya. Right, t minus 2. So that t represents Tanya's time. Minus 2 says 2 hours after Tanya has left. And again, y2 is equal to 4. So this equation for x would be 40t minus 80. Alright, so we're going to see if we have time to get this into that calculator. So go to your 2 equations. You're now plugging in 4 things. So 8t for Tanya and just a 2. You are traveling 40 miles an hour with that minus 80, and we're just plugging in a 4. And then if you go to the window, we'll just give Tanya 3 hours to run. We don't want her running for a long time, so we'll put a 3 there. We're going to change the t-step to make it a little slower to 0.05. We'll make the x min 0. The x max, if Tanya runs for 3 hours, 8, 24, we'll go up to like 30. And then the y max, we're only going up to 4, so you can make it a 5. Maybe we'll make it a 6 to be 1 more. That's just a 1. Questions? Okay, so before you hit graph, you need to go to mode. We usually graph sequentially, one after the other, but next to it, we're going to graph simultaneously. Don't press graph yet, because I need to tell you what you're going to see, and I want you to kind of understand what you're going to see. I'm going to press graph, so that you can kind of look to see what's going on. That's Tanya. The top line was me speeding by her. Your goal is to get them to meet, so that you stop and pick her up and you don't run by her and laugh. To do that, you need to press the on button when it looks like they're meeting. So you have to put a finger on the on button, put another finger on the graph. So you're going to hit graph, and then you're going to press on as soon as it looks like they are meeting up at the same point, so that you're not passing her, you're picking up your friend. You can make it slower, so you can make it 0.01. So you can change that, you can make it like 0.025. The slower the t-step, the slower your graph actually physically graphs.
Too slow.
So you got too slow. You can try it again by going back to y equals and just like typing the 8 over again, and it'll go down for you.
This is too slow.
Yeah, you go way too slow. Over here. Down the sequence. So do it simultaneously. So then after you have it, and they look close, if you go second quick, and then just type the T and hit enter, and it'll tell you your time. Minus 3 hours, because that was the max of my value. To find the actual time, you would take the 2 equations and set them equal to each other. And the time comes up to be 2.5 hours. Did anybody get close to 2.5?
2.5.
Oh, yay! So you guys are good. Perfect. So it takes you a half an hour to pick up Tanya. That means she's been running for 2.5 hours. She's almost run a marathon. Keeping that pace. Does anybody have questions with that? So you have two problems tonight. One is a state trooper trying to catch somebody who's speeding. The other one is two cars playing chicken with each other, which please don't do in real life. Your goal is to get them to meet. How long does it take for the cars to meet each other without like crashing into each other? Yeah, so it's in your packet. It's the next page in your packet, front back. There's a baseball problem on there. Most of that is just calculator work. However, the first two questions ask you to use your logical reasoning skills. We gotta do with those. Yes.
There was an extra credit problem in chemistry where we had a